much. So as I was introduced, I'm Dwayne. I live here in Chicago, Illinois. Happy to be joining you in this event from all over the world. I've been a developer advocate since 2016, talking about Git a lot of that time. You can find me on Twitter at MC Dwayne. Always happy to chat about anything tech related or anything else that I love, like improv or karaoke, rock and roll, knitting and crochet, which isn't on this slide. I have a wide variety of interests, but feel free to hit me up out there on the internet. These days I work for Git Guardian. Git Guardian is a code security platform for people using DevOps, what we call the DevOps generation. We do automated secrets detection publicly and for internal applications. So if you have secrets in your DevOps pipeline, which we all do, you should probably be using Git Guardian to figure out where those secrets are out in the world. So before we go any further, I would just like to say, anything I talk about today, the only way you will ever be able to ingest that and use it is to actually use it and get those commands in your fingers, get those concepts locked into your process. It was one of my favorite books because it's true. I can tell you about something all day. You can watch 100 YouTube videos, but until you start actually practicing, it's like any other skill, a lot of it's not going to stick. So this talk really is meant to be instructional at a very high level and point out a lot of concepts. But when we get to the actual practical, how to use some of this, you're just going to need to do it. Well, everybody here probably uses Git. If we were in the room together, I would ask everybody to raise their hand and ask, hey, who is not using Git? Java obviously predates Git by quite a bit. Git doesn't come around until 2005. It doesn't become popular until about 2008, depending on who you ask and how you count popular. But most of us at this point have adopted it, and most of the rest of the industry relies on it. And most of us can do, well, these basic things, and the concepts are pretty straightforward, cloning down a repository, adding, pushing. But then there's this whole other side to Git. Like there's a whole other world of commands out there in the world. And things like cherry picking and working in a detached head state, merge conflicts, that's where people start getting nervous and like, ooh, I'm not sure I really understand what's going on. And if we don't know how something works, it generally is a little bit scary to us, even if it's kind of harmless. And Git can very much seem like a dark art. It's got weird terminology like plumbing versus porcelain, trees and blobs. This is actually the description from the manual for Git rev parse. Pick out and massage parameters. Emphasis mine, but massage is the actual word they use there. And it just feels like it was written with a Linux power user in mind, because it was. These are the people that wrote it originally. The Linus originally wrote it for managing the Linux kernel project. Just how do you manage thousands of patches from hundreds and hundreds of people around the world? Well, that's what Git's for. A few months after he invented it, he handed it over to Junio there, Gitster, who still manages the project today. And for these hardcore Linux people, a lot of this makes sense. Now, the good news about Git is it is one of the most well-documented things that it was ever made, just from the way it got made. And it's open source. So you can go tear it apart, look at it. All the 4 freedoms are there. The bad news is it's written in C. A lot of it is anyway. There's a lot that's other languages, but going in and reading C is very hard for me. I am not a C programmer. But figuring out how it all works together can be a little bit overwhelming. And a lot of people learn Git a certain way with a lot of concepts and a lot of metaphors, because there are certain things that work sort of different in reality than they do in concept. And that leads to a lot of confusion, especially around things like branches. And that's one of the things I hope to clear up today and give you a slightly different way to look at how branching works. But if we just step back and look at what is Git's mission, what is it really doing? Well, it's just a file system tracker. That's all it really does. From a very high level abstracted view, it just makes a record of what has happened in a directory, when those things happened, and who caused them to happen. And if you were going to build Git from the ground up just off-the-shelf tools, these are the three main components I believe you would need. You probably need more than this, honestly, but the bare bones minimum would be a way to compress the file system very, very efficiently. A universal tracking system. We have a universal tracking system that we all agreed to for time. It's called Unix time. Every computer in the world knows what time it is. If you look up Unix time right now, it's like 1.6 billion something, but I'm not exactly sure what exact second we're on right now. Off the top of my head, I should have had that pulled up on my phone. And we need a way to write down where those archives are and what's in those archives. But that's really all Git does. Everything else is just figuring out how to manage that list of things and where to manage those compressions. One other really important thing with Git that makes it, I think, clearer, and they even say this on the git-sem.com website, up at the top of those rotating fun little slogans they have, everything is local to Git, everything. Whenever you get to a point with Git of like, well, I'm not sure what order things go in, always remember you're always local to whatever's checked out. Wherever here is to Git, that's where you are. So that picture below, why I like it in this context, is that is the here and there in Oakland. There was a writer one time who said, there's no there in there's no there in Oakland, or that's the problem with Oakland. There's no there. And some artists in the 70s made some here and there signs. So no matter where you are in the world, I'm in Chicago, I don't know where you're at, you are here to you, even though the here, the word here is in this picture on the slide on your computer. To me, it's there, but to you, it's there, even though those are different theirs. But your here is always here to you, no matter where you are. Even if you're there, to you, you're here. A little bit confusing, but more you just think, like, from my point of view, I'm always here. That's how Git always works. Git is the stupid content tracker, after all. If you just type man git into a terminal, you will see it says the very first line is Git, stupid content tracker. So let's take a closer look at Git internals. And when I say internals, I'm not talking about the actual C program language itself. We could get into that. That's a whole other world of talk. We're talking about the individual units of Git instances, and that is the project folders. So inside every Git project, Git tracked project in the world, every bit of code on GitHub or GitLab or Bitbucket or wherever, there is a Git folder, and that Git folder manages what's going on. And that's what we're going to take a look at. And from that perspective, that here, because that's really the here of Git, it's where it thinks you are. Before we look at that, the very first thing you probably did when you set up Git was you ran these three commands. When you download Git, the very first thing you have to do is tell it who you are. And that third one's optional, but we all do it now. We used to call the initial branch something else, and now we call it main. And we've all agreed to that, and we're moving on. But those first two make sense, again, if you step back and think about it from Linus's perspective. If you're managing patches for a project, well, Linus needs to know who you are and where your email address is so we can communicate with you. That just really works. That's just a really good system. It's a very simple signing system that's unique identifier of an email. Well, if we set those commands, we run those commands, we end up with something that looks like this. This is my Git config that lives on my home directory. And for me, it's my name. For you, it would be your name or whatever you call your home directory. I know this is on my home directory, and this is going to apply to everything because I'm setting it at global. But global is only one of the places that Git loads config in from. And I think it's kind of important to start out thinking in this perspective of, again, where is here from Git's perspective? And you notice it uses the term local in the middle there because local to it is the repo, the .git folder in the repo. System level tells your computer Computer specific things like mine references my OS keychain because I'm on Mac. Yours might reference something else if you're on a different system. Global are the variables we just looked at, and there's a bunch of more stuff in my config, but we're not going to talk about that in depth today. Local, like I say, is in the Git folder. You can actually assign config to specific work trees and all the way down to specific blobs. There are specific use cases for that, but for most people, you're not going to run into them. 99% of the time, you're probably just good at the local, global, or system level. You can see what's in yours right now. This is a read-only operation that just shows you what's there. That last one is my favorite, and it's the one I run the most often. When I'm curious, like, well, what config is my Git actually referring? Because config system list will show me all the config that Git knows about for that repo. So it will show me the global level, which is my keychain, my Git config. It shows me where the file is, all the way down, and it's not shown on here, but it will show me the local level as well. One of the cool things you can do with the local level, and we'll get to that in just a second, is set different username and signing keys and email there. So you can have multiple Git profiles just leveraging your local Git config. So now that we've got it set up, and that's a quick behind the scenes of where Git's even pulling its config from and why sometimes config doesn't work the way you expect it to, just go check the config folder inside of the .git folder. And this is what it looks like inside. And that's kind of all we need to know about that. I'm just kidding. I love that joke. There's a lot in here. And if you've never torn apart a Git folder, highly recommend it. Be brave. You can't break Git itself. You can blow up individual files, Git folders. But if you download something like an open source project, like, I don't know, just pull down some random file or repo from GitHub, you're not going to break it. It's not mission critical. So go and play with this all day. One of the key takeaways from looking in the folder, though, especially if you've never looked in here before, is the size of everything. Everything's very, very small. The biggest thing in here is index, and we'll get into why that's the biggest thing here in a second, but we're talking in terms of bytes, because most of these files are just a few lines of text. We have different folders, config, objects. We'll get into all that in a minute, but config is the one I have highlighted because that's my local config. I can put any specific settings for Git in that folder, and inside this project, they'll behave the way I want them to. But let's talk about some of those other files, like head. Head, one of the most important concepts in Git, because this is how Git knows where it's at. This is Git's point of view reference point. The head folder, or the head file, is very, very, very small. This is all it is. It's just, hey, the reference that I'm currently paying attention to, that is currently checked out or switched to, is this one, reference head main. Well, what does that mean? Where does that point? Well, that's where packed refs comes in. Packed refs simply is a list, a text list that tells, hey, here's where a reference pointer is pointing to, and this is a checksum. It's a hash that corresponds to something. But what does it correspond to? Well, this is probably a picture everyone has seen if you've taken any kind of intro to Git or studied it at all. Git, from a conceptual standpoint, takes complete snapshots of the file system over time. And it's very efficient at doing this. So between version 1 and version 2, the file A has changed. Now we got a version 1 of that file, but B didn't. B stays the same. Git is smart enough to say, hey, I need a brand new snapshot of this, but this, well, that's the same as that. So I'm just going to point back to the previous version and, oh, I need a new snapshot of this. And it will just take the pieces it needs and just make us a new snapshot of that. But what's in those snapshots? The actual files. This is why Git is great at working with text files and project files, but not great at working with giant binaries like pictures and movies. Once you start getting to a certain point, it doesn't really make sense to track those things in Git. And that's what things like LFS are for, but We're not really getting to large file system stuff today. But anyhow, Git will take your file, compress it down, run a checksum against that blob, that the compression, and then track those things and put them in a special file, a working tree that we can then commit and make a copy of that, a record of it, along with some metadata telling it who the author is, some other metadata, and let us write our own description of why we did that thing. So every commit is that full snapshot. And like I say, it works in the concept of blob, and you'll see this defined possibly different ways out there, but this is, I think, the most agreed upon reason it's called blob is binary large objects, which we then reference what's in those and where they are by a 40 character checksum that gets generated through SHA, the secure hash algorithm, which we're not going to get into the nitty gritty of how that works today, but that's where that number comes from. It's a checksum of those blobs. Very importantly, Git is not tracking the diffs. Diffs definitely exist, and Git diff is an extremely powerful tool. However, that is more of a mechanism to show the differences between those states. It's not tracking the diffs itself. You can always generate a diff, but a diff can be applied to something, but that's not the unit of transport. That's not the ultimate unit of storage. You can transport differences that way, but it's not the unit of storage. Where those compressed versions of your file go is into that index folder. And that's why index is noticeably bigger than anything else in the folder. So we're taking compressions of the file system at that point in time and pushing it into this special file called index. And you can look at index, but this is where, when you use git add, this is where it adds it to. For this particular project, I was working inside GitLens. The GitLens project was an open source tool, the extension for VS Code that makes it a little bit easier to use Git, in my opinion. This is what it looks like, and it's not human readable. There are human readable parts, don't get me wrong. There are the file names themselves, which don't get compressed, but everything after that, that's the actual file that's been compressed down. And Git's simply keeping track of what's all in there, and the checksums and all that are part of that data blob. So when we actually make our commits, that's where the object folder comes back into play, back in our look into our folder. So you'll see in the objects folder, there's all of these, two-letter file folder names. And inside of all those, you get like a crazy checksum here. But if you put those things together, the file name and the folder name, and compare it to like a Git log, you see something like, oh yeah, that commit is 39C385DC, 39C835DC. That's where it's stored. That's where the object is for the time being. Long term, it's probably going to end up in a pack file somewhere else, a little bit deeper in the file system. But for the next little bit, this is where it lives. And this is where it gets at, and this is what it's referencing. So it takes these snapshots, and like I said earlier, it will point back to the previous version, because Git makes these long chains of commits, these chains of references. And that's where our Git history is. It's just that chain of references. This is what we get when we run a Git log. Well, why we call it Git log instead of Git history? Why does it command that? Because we're actually invoking the log file .git/logs. And by default, if we just say git log, it throws out the head, because head is where we're pointing. And there's a special file called head that's like, hey, here's the master or the main view of the world. This is what git log prints. Specifically, git log prints the commits that happen in here. And I say, hey, well, what else is in there? Well, if you look at it and break it down, the format is starting ref, ending ref, the name of the person who made the commit or made the action, their email, Unix timestamp, UTC offset, and then the action performed. And pretty quick, you can tell, like, wait a minute, a lot of these have the same starting and ending refs. Git actually tracks everything that happens, not just commits. And then it keeps those things around for 30 to 90 days, depending on what specific system you're talking about and specific setups you're talking about. You can override this and make it keep around forever if you really want. Not a great idea, in my opinion, but know that no matter what you do in Git, you can always reference it for a minimum of 30 days. So if you completely blow up a repo and like, uh-oh, I really got to get back to that previous state before I did these very dangerous, undoable actions, undoable, true, that action, well, that happened. But we can jump back in time. It's one of the superpowers Git gives us. So run a Git reflog, and it will spit out, hey, here is exactly what has happened. But since we can't jump and check out those commits because, well, those commits are pointed at by head at the end of the chain of commits. Well, how do we reference them? That's what head at curly brace number means. So to move back in time, all I got to do is check out head at whatever numbers beside the action right before I did the thing that I want to avoid doing and get back to that state of code, that state of those files. In this case, I actually did that, and that's showing the power of this. I checked out one of these earlier to get at a earlier point, and then I checked out main again and moved back to a normal state. But if you've never done this before, highly recommend it. Again, just hearing me say this isn't going to give you a lot of action. Get it into your fingers. So the first time you do this, it's like, wow, it can really have the power to undo anything in Git. But if you do that, it's going to throw you into something called a detached head state, which isn't a bad thing. In reality, if you have something with a detached head, it's dead. It's not a good state. So it's a weird term, but in Git land, that's not parallel to our reality. Detached head simply means where head is pointed, where that head file is checked out, simply doesn't point at a pointer that points to the end of a chain of commits. So when you have a branch name, that branch name is simply a human readable, human invocable pointer that points to a commit. That's all detached head means. Now, how you affect that chain of commits from a detached head state, well, that tells you right here. You can look around, make experimental changes, and if you want to commit them, you can discard any commits. Made this, I kind of cut it off a little bit weird to make it fit on the slide, but it will tell you exactly what you can do in this state. You can make new branches from here. You can just copy paste into other branches, but it's a real superpower. You can always get back to a state that you were just at least in the last 30 days. But that raises an interesting question. So if those branch pointers are name pointers for a branch are just pointers pointing to the last commit, well, what makes a branch then? Conceptually, a lot of people have this in their heads. And there's nothing wrong with this, but this was not intended to explain branching. This explains a particular Git flow. In fact, it explains Git flow pretty well. But a lot of people, this is like, oh, well, branches are like these offshoots and merge and whatnot. I have a problem with this from the concept of thinking about what a branch is, because internally to Git, it looks a lot closer to this. Remember earlier, we need a compression, a time tracking system, and a way to write down what has happened. This is that notepad. This is Git saying, all right, well, we had a parent ref, and then there's the ref after it. So that's what happened, and all the metadata associated with that. And then we have human readable pointers that we can reference. So if I want to check out hotfix and make head point to that particular ref, well, all I got to do is check out hotfix, and then head will jump to there. If I want to check out feature branch 1, it's check out feature branch 1, or use git switch, which is a more modern thing to move head to point to here. So now I have head, which is a pointer that points at this pointer, which eventually points back to a commit. Commitish. That is what we call any kind of reference that eventually leads us back to a commit. It's one of those wonderful Git terms that nothing else really uses out there. A commit-ish thing, like a tag, leads us back to a commit. So a lot of things are commit-ish. But that's all branching really is. It's just a giant spreadsheet with pointers that we can read and move around, which I think makes this part make a little more sense. Merging preserves that set of refs you made that had a pointer to it. And until you delete that set of references and delete that pointer, they're just going to sit there forever. Rebase, on the other hand, takes that set of refs, that chain of refs that we have, rewinds time, because again, timestamp, we know exactly when we made certain changes, rewinds their time and replays those commits one after another through another branch, through another set of references. And we end up with a new clean straight line that has replayed all of those branches, but the process, that other branch ceases to exist. The branch pointer still exists, but the branch doesn't exist. And that's the key difference, I think, in understanding this, is you're not destroying the references, you're replaying the references, and the pointer simply just doesn't go away. It looks like this a little bit, maybe this will make a little more sense. So a merge is pretty straightforward. We make a branch, we make our changes, we keep working in main, and then we merge them together, and now we have a brand new commit called, well, main. It's C5 for the files we've changed. Pretty straightforward. But C4 keeps existing. Experiment still keeps pointing there. Rebase, well, we made that branch, we worked over there, we made some work over in main, and now, like, well, we don't need this over here, but we want all of these changes to now be in our main line of reality, this chain of commits. So rebase, let's rewind, apply those changes through with these changes, and we end up in a new state with a new pointer called C4 prime in this case. But that's where our experiment pointer points to. Unlike with merge, it didn't automatically combine everything. It just wrote them over what was here to get to a new state, and the pointer's still there. Meanwhile, main is still pointing where main was pointing because it's just a pointer. We then need to do a merge to make all of this come together, because in that case, a merge would say, all right, let's change where the pointers are pointing, but the code's all the same now. Great, let's just agree where the pointer points. That small little difference there is very confusing conceptually. And that's part of the reason I like to use GUI tools. I'm not a person that's going to tell you command line only. I'm never going to be that guy. There are awesome tools on it. Like I already mentioned GitLens, GitKraken. I used to work for them, but GitKraken's awesome. There's a ton of really, really awesome GUI tools to go out there and better visualize this and make it interactive. Because yeah, Rebase Interactive is another really good tool. So when you do a rebase, throw a -I, or again, use a GUI tool to use the interactive rebase modes, and it's going to make a lot of this make a lot more sense. And rebase will become your friend. But the biggest thing about rebase is don't rebase things that are public, ever. Rebasing is awesome for your personal work. One of the superpowers of rebase is squash. You can take a long chain of commits that you had that you made, like, yeah, one little typo. Oh, I fixed this other typo. Oh, I changed the README. Ooh, I realized I need to rearrange this one section. And you end up with like 12, 14 commits locally. Before you commit those and push that branch and that work to a public repo or to a private repo to share it with your colleagues, you can rebase and squash all of those to one thing and then just push that. And that's fine. That's awesome. I do that all the time because locally I make a lot of little mistakes and I like little chunks of work. But if you do that publicly, then this is directly from the Pro Git book. You'll be the scorn of your friends and family. So don't rebase work other people are working on. You can rebase a single commit, and we simply call that cherry picking. If you never cherry pick something, if you ever find like, hey, I made a commit and, oh man, I did it on the wrong branch. No problem. Check out the branch you wanted on and then just pull that reference over. Or you could do it from there with making sure you're referencing the target base. But just look up the docs. You're going to be a little better off for the actual commands there. All right. We're getting toward the end. I'm going to go a little bit quicker here. Merge conflicts. They're inevitable. They're going to happen. When you try to merge two things together, eventually Git's going to get confused. Because again, Git is the stupid content tracker. And as soon as it gets confused, it quits. But before it quits, it tells you how it got confused. So if you do a Git merge, I highly recommend fixing merge conflicts by hand, at least until you really, really understand what's going on. And then there's all sorts of tools to help you out, but I wouldn't jump to a black box. This fixes it for me automatically without understanding what it's fixing and how it's getting there. So when next time you hit a merge, do a git status, and git status will tell you what didn't get added to the index because it didn't know what to do. Look at those files that didn't get added to the index, that didn't get staged, and then go look for arrow space head, left arrow space head. This is where Git was. This is its point of view and what it thought reality was. And then here's the branch that you were trying to merge it with and what it thought reality was. And Git's like, I don't know. I'm just Git. I don't know. How do you fix this? Well, how would you fix any other text file? You would go in, say, no, I want Mundo to win. So I'm going to erase that line. 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 And then I'll get def hello, puts hello Mundo, end. And that's what I want. And what do I do after that? Well, I git add the file, and now I'm ready to commit and move on. That's all it is. Merge conflicts aren't a reflection of you as a developer. They are a reflection of Git not knowing what you mean exactly. And don't feel bad about them. Everybody encounters them, and you shouldn't feel bad or be scared of them. Git Worktree. One of my favorite overall things in Git is Worktree, and I use it instead of stashing, instead of committing things too early. By default, Git can only deal with one thing checked out at a time, which makes sense because we're tracking a folder. We're tracking the contents of the folder and the subfolders that the .git folder is in. So it can only check out one thing at a time. Head can only point to one thing. But Git has the superpower of multiple working trees. And as long as you assign a branch to a directory of its own outside of the main repository, you can work in those other branches. And Git is completely okay with that because it's a linked copy, but Git knows about it and knows how to manage a linked copy. And it doesn't interfere with the work going on in the other folder. So the work in this folder doesn't affect work in this folder, doesn't affect work in this folder. And those just all happen to be copies of the branches that are located in this folder. This one will make a lot more sense when you start using it, and I highly recommend start using it. So Git Worktree list always works. It will always show you where you're at and what trees are open. Git Worktree add, and then give it a path with the branch name at the very end. That will add things to that work tree. Then to work in that branch, instead of doing a git checkout, you just change directory over there and see it, you start working over there. And then you can git add, git commit there all you want. And when you're done with it, it's not a good idea to leave branches open the same way it's not a good idea to have long running branches for a project. At least that's what the DevOps people tell us with Accelerate and that kind of Dora research. But you're going to remove those open branches or those additional work tree entries as soon as you don't need them. And to do that, you just work tree remove in the same path. So next time you're at a point where like you're in dependency hell, where you can't stash, where you can't just walk away, make a new work tree, go work in it, and then come back when you're ready, and everything will be there. Git hooks, you probably know about. But you can make Git hooks do anything, which is kind of awesome and terrifying. It's a complete automation platform built into Git, and it's underutilized in my opinion. There's so many awesome things you can do with it. Build your own crazy contraptions like this Rube Goldberg device. There are 17 hooks available. The best resource I can ever point anybody at is githooks.com. Matt Hudson has done an amazing job of assembling a bunch of examples, a bunch of documentation for it. But there's 17 hooks available. 3 of them happen before a commit is made. So if you want to do things like checking for secrets before you actually make a commit to make sure you haven't hard coded a secret or an API key, a password or something, that's very possible. In fact, I work for a company that has a CLI that helps with that, but there's a lot of ways you can accomplish that. But know that if you can script it, you can make it happen. Last tool I'm going to talk about before we open up for questions is Git Bisect. This is not a tool you're going to use super often, but when you need it, this is a lifesaver. Git uses the power of halving to quickly figure out where something was introduced. It doesn't know what you're looking for. You can tell it what you're looking for, but this is a way for you as a human to quickly dig through a repo, especially one where the comment string is not, comments have not been very good. So imagine you hit a bug in production and you say, all right, where did this come from? Where did we first introduce this bug? You would simply tell Git, hey, Git bisect start. So we start the tool. Git bisect bad. Don't give it any other commands because we know head, where it's currently pointing, is bad. Then the last time you know that you had a good version, and you look back at the last release candidate and you say, okay, in this release candidate, it's not here. So we know that's a good state. So we tell it that tag is good. Then Git cuts the graph in half between the good state and the bad state. Doesn't matter if it's 10, doesn't matter if it's 100, doesn't matter if it's 1,000, doesn't matter if it's 100,000 commits. It just cuts it in half and says, hey, is this state in the middle that I'm checked out good or bad? And it waits for you to say Git bisect good, Git bisect bad. If it's good, it marks that as good and then cuts in half between the good and the bad space and does it all over again. You just keep repeating that. Through the power of math, you can't do more than 11 steps, no matter how big the repo is. Most of the time, you're going to find it in under 7. And it will get you the exact right place pretty quick. And then when you're done, you figure out exactly what commit it's from, and you've done your work to identify, wrote down what commit it was. Then Git bisect reset gets it out of there, and shuts down the tool and gets you right back to a good Git state. So in conclusion, go dig into the internals. You can't break Git itself, just individual repos. And if you're using like an open source project you're just pulled down just to experiment with, good for you. No harm done. Everything I'm telling you here is public knowledge through the Git book. Not everybody has time to read the Pro Git book, but it is free. It is a little out of date. The last version that's publicly available is 2014. Since then, we've done things like shallow clones, partial indexing. There's a few new concepts that were really invented for DevOps at scale. And if you need copies across thousands of containers of a repo, but you don't need the whole repo. But everything I talked about today is directly from the book. In fact, a lot of the examples I used were directly from the book, including that quote. And if you're at a point of like, well, I got the basics down, but I would love to start expanding out and using some of the other commands and tools, or you're brand new to all of this, and this is your first talk about Git, which I hope not, because some of this stuff might be confusing if you're not familiar with like git add and git commit. On the git-sem website, there is a link to this under documentation. It's one of the cheat sheets they link to. It's my favorite one anyone's ever made. It's interactive. You can click on a workspace or one of those columns, and it will tell you all the possible commands and where it moves the files in between. And there's an explanation at the bottom, very succinctly telling you what's going on. And there's a great resource called Dang It Git that sometimes we all get stuck. We all like, I don't know what to do. And Git's telling me this, and I'm not really sure what to do with this. dangitgit.com. It will tell you exactly what to do, because sometimes the right answer is, you know what? I'm just going to start over. Let's just kill this repo, reclone it, and start from there. And you know what? It's your repo. There's nothing wrong with that. Don't let anybody ever make you feel bad about using Git. I'm Dwayne. I live in Chicago. Hit me up on Twitter about anything. Always happy to talk. And now I will answer some questions if we have any out there. But that means I need to open up the chat. All right. Yeah, actually, a workshop on Git is something I'm giving later today. I'm actually participating in another conference as well here in Chicago, DevOps Day Chicago, and I'm giving a short workshop on some of the more advanced Git tools, like a few of the ones I talked about and a few others. And workshops are great, but you can also run your own workshop. Again, the Git book, just running through the examples in that and getting those commands in your fingers, especially around things like Rebase, are how you learn anything. Having someone guide you in a workshop situation is awesome, but really just spending the time on your own to go through the commands, I think is really helpful. One quick thing I will say on Rebase is using a tool like a VS Code with Git Lens. They have a really awesome interactive Rebase editor. It takes a little bit of funkiness to set up. You got to make sure like VS Code's in your path and you've set your Git config correctly. But once it works, it takes all the mystery away. Oh yeah, the way to get these slides, there sure is. I'm gonna take here and I'll share. Copy the link. Done. And I think I'm gonna put them here and send everyone a meeting. There you go. That's the slides I am showing you right now. All right. Any other questions? I know I threw a lot at you out there. So if there's any slides you want to go back and review, I'm happy to slide back through it as well. You know what, since we do have the time, let me jump over to my VS Code instance. Where is it? Oh, there it is. I can show Git Rebase -I. Oh, let's say, and here's the interactive Rebase. So I'm setting up an example here to do a bisect. Let me make this full screen. Oh, my screen sharing was paused. Screen share. You share. Okay, it's my desktop. Yeah. So here's what the interactive Rebase editor looks like with Git Lens. So I can pick one, I can reword it, I can edit it, I can squash it, fix up or drop those particular things I want to rebase onto my main branch. I'm not going to do it right now because I need this branch for later, but that's what that interactive Rebase editor looks like that I was talking about. Are there any improvements on large binary files in the last years? Glad you asked. Yes. LFS, let's type that Git LFS. Git LFS, I should probably put a slide for that in this talk, but it stands for Git Large File System. It's a function of Git that, I'll just Git LFS. Yeah. GitHub is the first one I know implemented this at scale. But essentially, instead of storing the blob or the very large binary in your Git repo itself, it makes a pointer to it and then stores it on a different file server somewhere else that's built for large files. GitHub includes, I think, a gig for free. All the providers provide a large amount of storage for free to do this with, because it's just such a common use case. And then instead of, like, say, a 10K or a 10 meg picture or video being stored in your Git repo, that video is actually stored in a different server. And then the only thing stored in your Git repo is like a 3-line pointer that just tells you where it's stored. And then when you pull it down, they have improved this in the last several versions of Git. One of the big issues around it is its fuzzy tool, which is how it interprets the file when you actually pull it in, and that underlying logic has been improved. I know that's something back when I was working at GitKraken they were talking about quite a bit, and I know they fixed that inside of GitKraken to make it a little quicker there. Always anxious to fix merge conflicts manually, and those UI tools are confusing most of the time. Which state is window part? Well, you're right. Just do it manually. Check in again. I completely agree with you. Absolutely. Anytime I hit a black box situation where I am not sure, like how it's doing it, it seems like magic, and I'm not sure what to do. But if I can do it manually, if I can do line by line debugging of like, how does it actually do this? It makes me feel a lot better. And it just feels empowering. And honestly, most merge conflicts you can fix a lot faster if you just do it manually, in my opinion. There are certain tools that give you like a left view and a right view. Tortoise Git has a pretty neat one, even though I'm not a huge fan of Tortoise Git and I don't use Windows. I just like their layout for it. It's like a left, an A and a B, and then an editor window at the bottom. And then you can simply say, oh, I choose that one over that one. But it's the exact same thing as going in manually and just erasing the lines you don't want. But if you erase the lines you don't want, then you have complete and utter control over what's going on. And I like that a little bit better because I'm a bit of a control freak, gotta say. All right. Well, I don't see any other questions out there. Yeah, thank you very much again. I'm very happy to be here, and always feel free to hit me up on Twitter, like I say. And with that, I think we can stop.